Hi, this is the second video of a playlist about the preparation of piperidines. As usual, you can find a PDF version of the slides under the Community tab of my channel. In this video we'll have a look at strategies for preparing piperidines with substituents at position 3. There is some overlap between the videos, so you may also check the other two for more ideas. Many alkaloids have a piperidine substructure. Despite the similarity, the mechanism of action can vary. Most natural piperidines are acetylcholine receptor ligands or sodium channel modulators designed to kill assailants. Here's a small selection of synthetic drugs containing piperidines substituted at position 3. These belong to a wide range of therapeutic areas. Some pyridines with substituents at position 3 are prepared on a large scale and are thus inexpensive potential starting materials for substituted piperidines. Ethylmethylpyridine and the vitamin nicotinic acid, for instance, are readily available. 3-methylpiperidine can be prepared by hydrogenation of a byproduct of the dimerization of acrylonitrile, another large industrial-scale process. Methylpiperidine is then converted into 3-cyanopyridine and then into nicotinamide. Quaternized pyridines are easy to reduce to either dihydro or tetrahydropyridines. These may serve as intermediates for preparing 3-alkyl or 3-aryl piperidines, for instance by Heck arylation or by conversion into an epoxide and isomerization to an allyl alcohol. 3-hydroxypyridine is readily available from furfural and can be used to prepare 3-hydroxy or 3-keto-piperidines, which are again potentially useful intermediates. 2-piperidinone can be obtained by reduction of 2-hydroxy or 2-aminopyridine, and its enolate can be alkylated, arylated or olefinated. Piperidines with substituents at position 3 can also be prepared by cyclization, for example by intramolecular Claisen condensation of the addition product of acrylates to primary amines. Michael addition of acrylates to aliphatic aldehydes yields oxoesters, and reductive amination then yields substituted piperidinones. Instead of aldehydes, also nitriles, amides or esters can be used. Another potentially interesting intermediate for substituted piperidines is the Claisen condensation product of pyrrolidinones with diethyl oxalate. Let's check some specific examples. This here is a somewhat painful preparation of 3-hydroxypyridine by sulfonylation of pyridine with oleum followed by nucleophilic substitution with caustic. Much easier is the conversion of furfural into 3-hydroxypyridines. Many variations of this transformation have been reported. In this example, hydroxymethylpyrrolidines was refluxed with methylamine and catalytic formic acid in aqueous ethanol, which gave a good yield of the quaternized hydroxypyridine. No oxidants or reducing agents were required. If a reduced form of furfural is used, oxidants will be required for the formation of hydroxypyridines. Aminomethylfuranes, for instance, can be converted into 3-hydroxypyridines by treatment with hydrogen peroxide and aqueous acids. Pyridines and pyridinium salts can be hydrogenated or reduced chemically to dihydro or tetrahydropyridines or to fully saturated piperidines. This is an example of enantioselective hydrogenation of a 3-hydroxypyridinium salt with the aid of a soluble iridium complex. No hydrogenation of the phenyl groups or the benzylic CN bond occurred. Under suitable conditions, such hydrogenations can also yield 3-keto-piperidines instead of 3-hydroxypiperidines. Here, a protected 3-aminopyridine was hydrogenated diastereoselectively with rhodium on carbon. Although the reaction was performed in acetic acid, no decomposition of the intermediate enamine occurred. The hydrogenation of nicotinamide or other nicotinic acid derivatives proceeds stepwise. The first intermediate shown here is a push-pull olefin, which is particularly stable. Being an aldehyde-derived enamine, it can be reduced with borohydride. Here, an enantioselective hydrogenation was performed with the aid of a soluble ruthenium binap complex. These here are optimized conditions for preparing a piperidine-derived epoxide and for its reaction with benzylamine. Pyridine was first quaternized with benzyl chloride and then reduced with sodium borohydride to an allylamine. The epoxide was generated by base-induced ring closure of a chlorohydrine. The reaction with benzylamine proceeded with high regioselectivity. In this example, a tetrahydropyridine was prepared as on the previous slide and then hydroborated with an excess and a high concentration of borane. One problem of large-scale hydroborations is that during the oxidation with hydrogen peroxide, hydrogen is liberated, which can lead to the formation of an explosive gas mixture. To lower the amount of hydrogen liberated during the oxidation, in this example, the intermediate borane was first hydrolyzed with aqueous hydrochloric acid. This must be done carefully to prevent protonolysis of the carbon-boron bond. Calcium chloride was added to trap fluoride. The final oxidation then yielded the secondary alcohol with high diastereoselectivity. Treatment of pyridines with an excess of a silane can yield silylated piperidines. Like boranes, also silanes can be oxidized to alcohols with retention of configuration, as shown here. Because of the large excess of expensive reagents, this strategy is a poor way to prepare the final product. I would instead test the hydrogenation of a 3-hydroxypyridine or pyridinium salt. The intermediate dihydropyridines formed during the hydrogenation of pyridines or pyridinium salts are nucleophilic enamines that can react with carbon electrophiles. Here, the first reduction was catalyzed by an iridium complex, and the required hydrogen resulted from decomposition of formaldehyde. Hydroxymethylation and further reduction then gave a 3-hydroxymethyl tetrahydropyridine. In this example, a dihydropyridine was generated by reduction of 3-chloropyridine with diethylsilane. The intermediate was then allylated twice with an allyl carbonate and palladium catalysis. This is an example of enantioselective rhodium-catalyzed Michael-type arylation of a dihydropyridine with a boronic acid. Both yield and enantioselectivity were excellent. Heck reactions with tetrahydropyridines, like the starting amine of this example, can yield either 3 or 4 arylated products. Here a mixture of 2 3-substituted tetrahydropyridines resulted. As discussed in part 1 of this playlist, protected piperidines can be lithiated and then alkylated or arylated at position 2. In the presence of palladium catalysts, however, sometimes piperidines with substituents at position 3 are obtained, as in this example. Presumably, these products were formed by isomerization of alkyl palladium intermediates. 2-piperidinones can also be suitable starting materials for substituted piperidines. Here an enolate was generated in the presence of one equivalent of a chiral chelating amine, and benzylation by benzyl bromide proceeded with high enantioselectivity. The starting piperidinone can be prepared by oxidation of 1-methylpyridinium chloride, as shown in the first video of this playlist, followed by hydrogenation. In this example, 2-piperidinone was protected and activated by trifluoroacetylation at nitrogen, and then condensed with 4-fluorobenzaldehyde. Enantioselective hydrogenation with a soluble iridium complex then gave the target piperidinone. These can be reduced to piperidines with lithium aluminum hydride or with borane. Still more acidic than simple 2-piperidinones are 3-alkoxycarbonyl piperidinones. Here a mentyl ester of such a piperidinone could be fluorinated with high diastereoselectivity and then reduced to a 3-hydroxymethylpyrrolidine with borane. Suitably protected piperidines can also be oxidized and acylated at position 3 directly. Here an alpha-keto acid was used as a source of a benzoyl radical, which then added to an intermediate enamine. With acetophenone and tempo instead, diketones can be obtained in moderate yield. Still, this is a quick approach to potentially valuable intermediates from inexpensive starting materials. Similarly, protected piperidine can be nitrated at position 3. Reduction and Neff reaction then yielded protected 3-keto-piperidine. Let's check some cyclization reactions. Pentenyl-amides can undergo intramolecular acyloxy amination of the CC double bond when treated with oxidants. In this example, a diacyloxyiodobenzene and catalytic copper 1 were used. Here, a similar cyclization was brought about by treating the pentanylamine first with NCS and then with a mixture of sodium acide and iodide. An acidopiperidine resulted with high diastereoselectivity. Amines can also react with internal alkynes, either by direct nucleophilic addition or by electrophilic attack by an iminium salt. Here, the latter strategy was used to prepare an iodinated 3-ethylidene piperidine. Many strategies are known to prepare oxoesters suitable for the cyclization to 2-piperidinones. Particularly convenient is the Michael addition of an acrylate to aldehydes, ketones, nitriles or esters. In this example, phenylacetone was added to a serine-derived acrylate. Enzymatic reductive amination with a transaminase gave the target piperidinone with high enantioselectivity. In this example, the initial Michael addition was between a cinnamic aldehyde and a malonamide. With the aid of 8% of a proline-derived catalyst, a substituted piperidinone resulted, which was used as intermediate for the preparation of paroxetine. One intriguing way to prepare 4-aryl tetrahydropyridines is by heating alpha-methylstyrenes with formaldehyde and a primary amine. Under optimized conditions, it is even possible to hydroxymethylate the initially formed tetrahydropyridine once more, as shown here. Again, the product was meant to be an intermediate for paroxetine. The yield was only low, and an important side reaction was probably aromatization to the pyridine by hydride abstraction with formaldehyde. Reaction of 1,5-dihaloalkanes or related dielectrophiles with primary amines usually gives high yields of piperidines, and only small amounts of linear oligomers. After the first CN bond formation, the second one is sufficiently fast to prevent reaction with the second molecule of dielectrophile. In brackets, I've sketched 2 further types of dielectrophile suitable for the preparation of piperidines. In this example, the dielectrophile was an alpha-bromopropyl acrylate prepared by radical addition to styrene. The amine added faster to the CC double bond than to the ester group, and a mixture of 2 diastereomeric 3-ethoxycarbonyl piperidines was obtained. Also 1,5-disulfonates can be convenient dielectrophiles for preparing piperidines. Here, an enantiomerically enriched 1,5-diol was prepared by hydrogenation and simultaneous dynamic kinetic resolution of a lactone with a chiral iridium complex and 1 equivalent of potassium terzbutoxide. Conversion of the diol into a dimesylate followed by reaction with propylamine yielded the expected piperidine. Here, an amine was first added to an acrylate, and the intermediate ester enolate was then treated with 1-chloro-3-iodopropane. All this was done in the presence of a slight excess of a chiral chelating ether, and the reaction proceeded with high enantio and diastereoselectivity to yield a thermodynamically less stable cis isomer. Epimerization then yielded the more stable trans isomer. Glutamic acid can be transformed into the starting pyrrolidinone of this example. Treatment with quaternized DMSO and a strong base gave a carbene precursor, which cyclized to a 3-piperidinone upon treatment with catalytic iridium. One convenient strategy to prepare 3,4-mil tetrahydropyridines is by intramolecular aldol condensation. Heating acrolein with glycol and hydrogen bromide yields 2-bromoethylldioxolane. Twofold alkylation of primary amines with this bromide gave an intermediate which cyclized in high yield when heated with hydrochloric acid. Intramolecular Claisen condensation of alkylated glycine esters, like the starting material of this example, can in principle yield 2 different ketones. Interestingly, however, only one of the 2 possible isomers was formed. Decarboxylation then yielded a 3-keto-piperidine, and upon reaction with phenyl magnesium bromide, the expected tertiary alcohol. 4-piperidinones can be alkylated at position 3, either via ketone enolates under alkaline conditions or with iminium salts under acidic conditions. Here, the latter strategy was used to prepare a bicyclic piperidine. The keto group was then reduced with the Wolff-Kishner reaction. Because bridgehead enolates do not form readily, the strongly basic conditions of this reduction did not fragment the 4-piperidinone by beta elimination. This is an example of a cycloaddition yielding a substituted dihydropyridine, which should be easy to reduce further to the piperidine. The dihydropyridine was formed by heterodyls-alder reaction of an acylated alpha-beta unsaturated oxime with a simple alkene, followed by beta elimination. Let's have a look at some potential side reactions. Alpha-aminoketones are reactive compounds that readily undergo a number of decomposition reactions. Despite its protection as benzamide, the starting ketone of this example underwent clean autooxidation and ring fission in the presence of bases. Nucleophilic substitutions at position 3 of piperidines sometimes yield substituted pyrrolidines instead of the expected piperidines. These ring contractions proceed by intermediate acyridine formation, as sketched here. The reverse is also true, and nucleophilic substitutions at activated hydroxymethylpyrrolidines can yield 3 substituted piperidines. 2 or 4 methylpyridines are acidic and easy to alkylate, acylate or olefinate at the methyl group. 3-methylpyridine is much less acidic, though. Lithiation of the latter yields a highly reactive intermediate that tends to dimerize before reacting with other electrophiles. 2 examples are shown here. Lithiation and derivatization of 3-methylpyridines may, however, succeed if the electrophile is stable toward bases and already present during deprotonation. Here's a selection of mostly newer references, which you can also find in the description of this video. Under the Community tab of my channel, there's a PDF version of the slides. The next video of this playlist is about the preparation of piperidines with a substituent at position 4. See you then.